So to motivate this unit, I want to kind of ask a simple survey question. How many of you all like video games? Okay, about 50% or maybe more. Do you all know how video games actually operate underneath the computer?
Ones and zeros.
Sorry?
And ones and zeros.
Okay, ones and zeros. That's how the computer works. But what are the calculations that the computers run?
I mean, it depends on the nature of it's right. Like if
I have a plain request for you. If you want to talk, you got to be loud. Even I'm not able to hear
Okay.
you.
so basically it depends on the game engine that you're running. Some of them do stuff slightly differently, but generally you have like a physics engine that'll be running physics calculations for all your models and stuff.
Okay.
You'll have like video, or I guess you could say graphical engine stuff, which
So let's take it one step at a time. You have a physics engine which makes some calculations, and then your Angry Bird or your missile or your bullet, whatever it is that is moving on the screen, it is moving from point to point. It's an animation that is being rendered, and that animation needs what? If you want to make a movie, what is that you need? Those who are into filming,
frames.
frames. What is a frame? Like what is the information that is in the frame? If you have some object of interest, you need to have its position at a given time point. And in this, let's say this is frame 1. In the next frame, it has to have the position at the next frame and next frame and so on. So you go from here to here and here and do something. That's how you construct movies. So what's the difference between filming a movie and creating a video or creating an animation?
You have active inputs and then
1 second. We went up first. Yeah.
The movie is a set recording that will not change, whereas in a video game it has to be able to adapt to user
Inputs. And a movie is something you go out and acquire at a certain rate. An animation is a set of calculations that you visualize at a certain frequency. And that frequency is usually the refresh rate of your monitor. Okay. So and the other point you said about the user inputs. That is, you are the controller. You use your gun to take aim and then release the bullet or the missile or whatever it is, and it has to travel in the trajectory. Sometimes they try to make it very realistic by factoring the prevailing winds, or whether you're shooting it from under the water or from the ground or above the ground. You can make it as realistic as you want. And where does all of that complexity go? It usually is stored in what you called as the physics engine. It's where all the physics lies. Let's stop there for a second. So this point is clear. We have to compute trajectories. Trajectory meaning where will the particle be, or where will your object of interest be as a function of time, and what will its instantaneous velocity be, what will its instantaneous acceleration be, so that you can advance it from frame 1 to frame 2 and 2 successive times. Is this concept making sense to you? Okay, think Angry Bird, simplest video game that you can imagine. It's like in good old days when I was a student, they used to teach projectiles by asking you to take aim at a certain angle and then asking us to calculate where it will reach the maximum and with what speed will it come down, what will happen if there is a wind going this way or wind going this way, and so on. Now you have Angry Birds game to visualize. You want to reach a target that is here. Should you aim like this? Or should you aim like this? Do you want to cover distance, or do you want to cover height and speed? That's your hook. I want you to keep thinking of Angry Birds as we go through this unit. Okay. All right, come back to physics engine. What is physics engine? Let's uncover that term and talk about how do you simulate physics? Yeah.
physics equations.
Sure, that's a fair assumption, but what are those physics equations? Kinematic equations, can instead of giving me names, can you tell the equation? See, this is the problem. Not that you are the problem, I'm saying you want to know the concept, not the names. It's okay if we don't call it physics engine or kinematic equations, but we want to know what is it that we will solve in order to compute trajectory. How do you compute trajectories? Yes,
Position, velocity, and acceleration equations.
what are those? What are those?
Equations of movement.
So if you go back to your mechanics, I'm sure all of you have studied Newton's second law. Mass times acceleration equal to the total force acting on an object. Okay, that is the equation, and you can write this as either m dv dt equal to force, or you can write this as a second order equation, m second derivative of position equal to force. Ultimately, you want to solve this for velocity as a function of time and then position as a function of time, so that you can render it and turn that into a video. Right? This is what goes into your physics engine. Now, you talk to me about what type of physics would you imagine in this example I gave about Angry Birds. What are the kind of physics that you can think about? What all is going on when you launch that little birdie at an angle with some initial velocity? What all can happen? Sorry, come again. Free flight motion, what is that?
How it flies through the air.
How it flies through the air is the resultant of all the forces that act on that object or bird. Can you list for me what are the possible forces in this example that can act on this bird? Let your imagination run. Yeah.
I think for your example, you just want F computer force of gravity.
Okay, so first on the list is weight or gravity.
The applied force rather than like a slingshot.
The slingshot launches you with a velocity and stops acting on you. It's no longer in contact with this bird. Once it's launched, there is no force. So while this bird is in flight, there is no force due to the slingshot. What else?
Resistance.
Air resistance. Okay. How do you think about air resistance if you have taken fluid mechanics already?
It be like the fluid's resistance. Or I don't want to say.
Yeah,
resistance,
that's
but
correct.
fluid's
Fluid resistance.
Opposition to motion.
So you can write the air resistance is a force that is generally opposing your motion. Okay, yes,
Similar but not exact is force of the wind.
wind force, that is, I mean, it's similar in the sense if the wind is helping you, you wouldn't call it a drag. But if the wind is not helping you, you call it a drag. It's just a matter of name. So we'll include that here also. Usually it's written as V minus the local air velocity. Yeah,
Impact of the environment.
elaborate.
The mass of the bird is going to collide with the standing blocks and cause them both to be displaced.
Sure. So you're talking about collisions.
Yeah.
So you have a block here, which let's assume when something hits it can fragment into two pieces. So you have your bird hit the block goes into two fragments, your bird may rebound and find another spot to finally rest. Something like that. So you have to model collision physics. Collision. So instead of going into too much detail, at least from your dynamics course, may I ask you what are two types of collisions you have heard of?
Elastic, plastic.
Elastic, plastic. Can you tell me what those mean?
Essentially, if energy is conserved or not.
Energy is conserved all the time. It's momentum that you're talking about. If momentum is conserved, it's called an elastic collision. If two particles come together, stick together, and then never separate, that is called a plastic collision. Okay. All right. So thank you for the inputs. What you are seeing here is a list of forces that are applicable to this situation. You can generally think about trajectories or think about forces on particles for many contexts. It is not just, so think about an example, like for example, if you have a snooker table and you're seeing the top view here, you have a white striker, and then you have your set of different colored snooker balls that are arranged, and then you tap it with your, what do you call it? Cue or stick, whatever. So it goes and impacts these spheres, and then they all go their separate ways. Some of them collide with the wall, get reflected. Some of them collide with each other and then get scattered. Some of them go to the corner and find their spot in the holes. So if you have to run a simulation of this, how do you think about these, say, ball and wall collision and ball and ball collision? Yeah,
Elastic.
you can think these are elastic because that they make, by design, they make those balls really shiny and smooth, so that when they bump off of each other, there is very less loss in momentum. So you can come up with a model about how the collision happens between two balls. You can also think that when they collide with the ball, have you touched the inside of a snooker table? Has anyone tried? How does it, what is the texture like?
It's
Soft.
It's like velvet. It's like very smooth velvet. So
There's not a lot of resistance.
there it is by design that it's not a lot of resistance, but eventually the balls will decelerate and come to a rest. So you have to think of a model for friction, that is friction between the balls and the snooker table. So a lot of what you called physics engine is about trying to figure out how to express the forces at work in mathematical form. If you are able to do that, you can set up a simulation which generally looks like this: mass times acceleration equal to force, and force is a long list of all the possible terms. Okay. Another example you can think of is, I'm sure we have all been to parties, we have all played air hockey. How does air hockey work? There's a lot of fluid mechanics in air hockey, if you are still sober enough to pay attention. Yeah.
The table has a lot of very small explosions with air is pumped, which come through, creating a buoyant situation.
Like an air film.
Yeah.
It's an air film on which your disc is almost floating through without touching the surface. Most often it is not touching the surface. So you get a big break on the friction. Break meaning big reduction on friction. Okay. All right, so that's hopefully that got you interested to study ODEs. Okay. What we are trying to do in this module is to solve ordinary differential equations, which can either be stationary, meaning they are between two position variables, or say, for example, dy by dx equal to f of x comma y, where x is a position variable, or they can be time dependent, dy over dt equal to f of y comma t, where t is time, which means what? Time can only be positive, and in a simulation, time can only involve the current and past. It cannot involve the future because you don't know the future yet. So only current and past is known. Past is known. Here, if you have a domain, let's say you have x equal to a and x equal to b. Usually, the value of y or its derivative y of a and y of b is given, and these are called boundary values. These are called boundary values. So in order to solve this problem, you need to tell what are the values of y at least 2 points, so that you can solve for what happens between a and b. So this type of stationary problems is a boundary value problem. Okay, and when it comes to time domain problems, you have to specify what happened at an initial time, say t equal to 0. You have to say what was y of 0. So you have to tell what is the initial value, and so these problems are called initial value problem. Give you some time to catch up writing here. So usually these type of boundary value or stationary problems occur when time is not relevant. Okay, can you give me any example where you can think of a equation that looks like this? Dt over dx equal to something, or d squared what do you use in solid mechanics for deflection? D squared theta over dy squared equal to something. So usually they have some kind of a gradient, and let's say this is the temperature along a bar where the temperatures at the ends are known, and you are asked to calculate what the temperature profile, something like that. You can also apply the same type of thinking for deflection problems, where you will be specified a load or a deflection at the ends, and or somewhere in between also, and you'll be asked to solve for the deflection profile or the load profile along the beam. So examples. Temperature profile along a bar. Deflection of a beam. Those type of stationary problems. The video game example we saw today is almost exclusively the time dependent or initial value problems, where you are asked to calculate what happens in the next or future instance of time, given that you are told what was the initial condition. So this is about prediction. This is about telling what happens next. So here is maybe I should do this as a class participation question. So why don't you all take a sheet of paper, put your name down, and I'm going to ask you one question. You're going to answer it on the sheet of paper, pass it back, and we'll count that as today's participation. One sheet of paper. So for the next 5 minutes, please don't have any discussion, just whatever you think, write it down on your sheet. Let me write down the question, okay? So boundary value problems look like this: dy by dx equal to f of x comma y. And initial value problems look like dy by dt equals f of y comma t. In both cases, your goal is to solve for y at a given range of x or y for times greater than 0. That is your goal. Okay, and what we will do is we are going to use approximations of this derivative using what we learned in numerical differentiation. So in numerical differentiation, what did we learn? We try to say dy by dx is approximated as, say, yi plus 1 minus yi multiplied by delta x, something like that. So what I'm asking you is, for boundary value problems, so let's say we have backward differencing, we have central differencing, and forward differencing. What you need to do on your sheet of paper is put this table, which is 3 by 2, 3 columns and 2 rows, and you have to say possible or not possible. Whether it is theoretically possible to use a backward differencing scheme in boundary value problems, in initial value problem, central. So for each block in each box, you just have to write yes or no, possible, not possible. That's it. So 6 entries. Think and write. There is just a small trick. No, what's the question?
Do you want us to list for justification why?
No justification. Just say yes or no.
You said backward, central, and what's the last one?
Forward.
Okay, thank you.
You don't have to justify. You just have to write yes or no down, and then we'll talk about the justification. So 5 minutes. If you're done, pass on the sheets to me. I'll take them. 6 entries, yes or no, 6 times. That's all. Yeah. Yeah, I'll give you. Please don't forget to put your name.
I'm a little confused about the question. Wouldn't it matter just dependent on which point or?
The question is it possible or not possible? What is optimal or ideal is not the question. Oh, okay, you are asking, like, let's say you are somewhere in the middle of your spatial or your temporal domain. You're not at the edge. You're not near the edge. Okay, 5 minutes of work for one person doesn't get that. Say it again. Let's stop it. Do your best and then we'll talk. It doesn't matter if you are right. Everyone has given this back. Thank you. You all given it back? Your sheets. Okay, so now let's talk. If you're thinking about boundary value problems, what Omar asked here is like, I think he's worried about. Here is my domain, x equal to a and x equal to b. If I'm in the middle somewhere away from the boundaries, I can approximate this derivative using both my forward neighbor and backward neighbor and the current point. So I can either do, I can do backward differencing, forward differencing, and central differencing. If you are in the bulk. You understand what I mean by bulk? You are somewhere in the middle, in the thick of it. If you are near one of the boundaries, especially the right or the larger value, if you are at x equal to b, of course you can do backward and central, but not forward. And if you are at x equal to a, you cannot do backward, but can do central. I'm sorry, you can't do central either. You cannot do central, you can do forward. But what I was looking for is this bulk only, so I don't care if you didn't worry about this, but just be aware. Initial value problem is all about predicting the future which doesn't exist yet. So there is no scope of doing forward differencing. Doesn't exist. How can you get values that don't exist? If you can't do forward, it also means you can't do central differencing because it is predicting the future. It's a time dependent problem. No central either. So your only option is to go backward. So this is the expected answer. Again, if you are here, you submitted your work and you missed one or two, we would forgive all that. All it matters is that now you know this. Okay, so you have participated in this class. Okay. All right. Yeah.
But if we're like for IVPs, we're at 0, we can't go back and stick those statements, yeah.
You cannot, you don't have to solve it at y. Here's the question he is asking at t equal to 0. I can't solve it. You don't have to solve it because this value is provided to you. This is part of your initial value. By the same logic, in boundary value problems, you don't have to solve it at x equal to b. You have to solve it only at least one point adjacent to x equal to b. So you can do central differencing, but of limited accuracy, not like higher accuracy, not with the same accuracy you do in the bulk. Okay, So this is like, maybe not, it's a tick, but like saying limited accuracy. Limited accuracy. Yeah. All right, so anyway, if you have submitted your work, you will get credit. Okay. So now let's get into the actual equation solving. We want to start with a stationary problem, and we want to see how to solve dy by dx equal to f of xy in a domain. So as we usually, like we did for integration, we want to select an example for which we know the answer, and then we'll use it to check our work. So the example we have in the book. Dy by dx equal to minus 2x cubed plus 12x squared minus 20x plus 0.5.
Where in the book is that coming from?
This is the first example it's in section 25.1. I think, let me just make sure, because I'm using the next edition. It is okay. So this is not 0.5, this is 8.5. So we will stick to this example for a while and use different methods to solve the same problem and see how the accuracy improves slowly. Okay. So this is your equation, and if you have to analytically solve it, if you have to solve it, y of x equal to x to the fourth over 2 plus 6x cubed, right? No, sorry. 4x cubed. 4x cubed minus 10x squared plus 8.5 plus a integration constant.
That's 8.5x.
0.5x plus constant. So we are told that y of 0 equal to 1, which you can use to solve for the constant c as c equal to 1. So your analytic solution, or y exact, is ready for us to keep aside and then do the numerical solution. So the first of the methods we learned, Euler's method. It's the simplest you will see here. Section 25.1, Euler's method. It's like writing dy by dx is approximated as yi plus 1 minus yi divided by delta x. And then you have dy by dx equal to f of x comma y, that's your ODE. So it's yi plus 1 equal to yi plus f of xi yi multiplied by delta x. This is Euler's method, which uses a forward differencing approximation for the derivative. So this is where I think the book is slightly misleading you in using the symbol X for these type of problems. Where in this statement, the way it is written here with forward differencing, it is meaning like here is x equal to 0. You are say this is I equal to 0, then I equal to 1, I equal to 2. You are calculating the solution from step to step, and you are forward stepping. That is, you are going in this direction in increasing x, kind of like time. It is actually a time dependent problem, but they state it in terms of x, which makes it confusing. So we'll call this Euler's method for initial value problems. So you could equivalently write this as also dy by dt equal to f of y comma t, and you can write yi plus 1 is yi plus f of ti yi multiplied by delta t. So both these are equivalent here, at least in this section. So for the problem we have chosen as an example, we want to solve for x equal to 0 to x equal to 4 in steps of delta x equal to 0.5. So you want to solve it for x equal to 0, which you already know y equal to 1, x equal to 0.5, 1.0 all the way up to 4.0. What would be the value of y in each? So let me write out a table. Let me write a table here. X, y, 0.0, 1, 0.5, 1.0, 1.5, 2, 2.5, 3, 3.5, 4.0. So you want to fill this out, which at least for one value we'll do it manually, and then we can start setting it up in Excel. So how would you compute? So if you put it as a grid, how do you visualize this? This is 0, 0.5, 1.0, 1.5, 2, 2.5, 3, 3.5, 4. This is your known value y equal to 1. Just take a pause from the writing, look at this statement, and geometrically, what does that statement represent?
It's the same here, last step plus the function value times your step point.
What is the function value? The function value is not just some value, it has a specific meaning. What does that mean? If you are here, say your y value is 1, okay, at the next point we are taking this point and then multiplying it by the slope times delta x, which is this value. So this is delta x, this is slope. What is the local slope at this point? What is the local slope at this point? In any point? It's the derivative dy by dx at that point, x equal to 0. Well, dy by dx happens to be this function. So this is not just a function, it is the function. Okay. So this slope here is dy by dx at that point, which is nothing but f of xi comma yi. So you are adding yi plus slope multiplied by step length. How do you express it mathematically? Yi plus slope being dy by dx at I multiplied by step length being delta x. This is this one. And this is yi plus f of xi yi multiplied by delta x. Where is this coming from? This is the ODE. That is the statement of the ODE. Do you see that? There is, I'm not pulling this some magic by saying dy by dx equal to f. That is what the original problem is. The slope is given as this function. Now solve for y. That's what you are asked to do. So we are using the function to write the value at the next point is the value at the current point plus the slope multiplied by step length. So at here you have yi plus 1, which is this formula. Whenever you do these numerical methods, you have to have some geometric sense of what's going on here. You are taking the value, adding slope times step length, and essentially this part here, this segment is this segment. That is the change in y. So if I call this delta y, which is yi plus 1 minus yi, this segment is delta y. Can you, I'm seeing a lot of blank expressions, so I want somebody to speak up, tell me whether this makes sense or not. Can you agree with this at least? So whenever you are trying to advance the solution, from here you would take this point, the slope at that point, which may be something like this, and advance it to the next point. And then there on the slope might be this, go on to the next point, go on to the next point, next point, next point, next point, and so on. You're just taking one step at a time and projecting forward. Okay. So how would you compute y at 0.5? Y at 0.5 should be equal to y at 0 plus f of x y at x equal to 0. How do you evaluate f of x y at x equal to 0? Given right there, this is f of x y. Don't look at this analytic solution, you don't know it. The whole point of learning numerical methods is to deal with situations in which we don't know the analytic solution or can't get the analytic solution, which is most of the time for us because we are engineers. So this is f of x y. So what is f of f of 0? 8.5. You just have to substitute x equal to 0. Y doesn't appear here, so it's 8.5. So this would be y of 0, which is given as 1 plus 8.5 multiplied by step length, which is 0.5. So what is the value here? What is half of 8.5? 4.7, no. 4.25. Thank you. 1.425. 1.4250. Now, can you please compute this for x equal to 1? If you substitute x equal to 0 here, you are left with 8 points.
And the y just comes from the initial condition.
Correct. Correct.
Would always be.
It's given in the problem. It might be 42 for in some other problem. It's given as part of the information that is known to us. Say, to give you an example, in our department, we don't have a measurements class. We have fluids lab, we have thermal lab, we don't have a mechanical measurements course. In Minnesota, when I was a TA, I used to be TA for that course. Every student has to do like a homemade measurement project. You have to come up with a situation, do a measurement. Most often what students will do is they'll buy a thermistor which costs like $1. They'll dip it in a coffee cup and observe the temperature profile. So the reason I bring that up here is, if you were to model that problem, what is the one piece of information you need about the experiment? You know it's water. You can look up the thermal conductivity, the heat transfer coefficients and so on. But what is specific to the experiment you need to look up or you need to know? If you are to predict temperature, how temperature cools down over time, what about that situation should you know? I can hear your
The
lips
accuracy of
moving.
the tools,
Sorry?
the accuracy of the tools that you're using.
No, you need to know the initial conditions. You need to know whether the water was at 35 degrees Celsius or 100 degrees Celsius. You need to know the initial temperature, which is very specific to that experiment. If you do the experiment and I do the experiment, everyone will get different initial conditions. But these type of initial conditions or boundary conditions, they are all specific to situation. They can't be generalized. That's the moral of the story. Don't expect y of 0 to be 1 or a specific value all the time. Okay. All right, what do we get for 1.5 or 1? 2.175, and you can see where this is progressing. You can use this. You can use this to construct an entire table, and you can verify that against example 21 or 25.1. Wait, you're getting 5.25. That's what the book also says. Okay, 5.25. So 5.25, I'll give you all a minute more to make sure you are getting this. Those who are trying, if you can't get this number, that means we have to talk again. Okay, so please try. Yes. Yep, it's given. So that you don't have to do anything about it. Yeah. Are you able to get the subsequent values? So for 0.5, we are expecting 5.25. And for 1, we are expecting 5.875.
Yes.
No.
5.22.
So along with the values, I also want you to compute what is y exact at each x value and put it along here. So if you take 0.5 and put it in this y exact, what will be the number? Can you also write that in? I'm going to make an Excel sheet for this, but I want you to do the hand calculation. So this is y Euler's method, okay? Euler's method, which uses forward differential. So what is y exact at 0.5? Y exact at 0.5,
I got 3.125.
3.125. And at 1.0, that should be easy,
Which is great.
3. So you can compare 1 minus y Euler divided by y exact expressed as a percentage. It doesn't apply for the initial condition because here at x equal to 0, there is no computation going on, it's given to you. For the next rows, what is the percentage difference? So that is 1 minus 5.25 divided by 3.125 expressed as a percentage, and 1 minus 5.8750 divided by 3 expressed as a percentage.
We get a very big number for the first difference, right?
Yeah, it should nearly 2/3. The book says minus 63.1%. And for this point, minus 28.1%. So try to get up to here, those who are doing it manually. Those who have your laptops with you, try to open Excel, set this up and fill out the remaining table. Go ahead. Yeah,
I'm not sure why, but I'm getting 68% difference for exact 0.5 between the exact and the other.
you mean this when you evaluate it 68?
68%.
My eyesight is fine. Let's give us a minute, we'll check it out. So this might look very too basic, but trust me, it will get pretty ugly pretty soon. So I'm going to have my x, y Euler, y exact, and then percentage difference. So those who are those who want to do Excel but are struggling, I'm going to do this with you one step at a time. So if everybody's okay, I can bring down the projector. Is anyone still writing? Okay, good.
Exact time.
Okay, so I'm doing this for those who generally want to do but struggle to keep up with speed or for any other reason. Okay. All right, our x values are starting at 0. They go in increments of 0.5. So you just take the previous value and add 0.5. Okay. So I'm going to drag this down few more rows until I get up to x equal to 4. All right. And then for the first row, this is initial condition. So I don't have to do any calculation. I just have to enter 1. Exact value is 1. Difference does not apply. Initial condition. All right. And then the other easy thing to do is we can punch in what y exact must look like, which is we just derived it. I'll write it here, or if it will be on your notebook, I think. Minus half x to the fourth plus 4x cubed minus 10x squared plus 4x cubed minus 10x squared
8.5x.
plus 8.5x and then plus 1. Okay, thank you. Plus 8.5x plus 1. So you got to go to column E equal to minus 1 by 2 times x to the fourth plus 4 times x cube minus 10 times x squared plus 8.5 times x plus 1. So those are your exact value, and you can drag it down to populate the other rows. Is this correct? Am I making some mistake?
You might have a notation error on the 1/2 is a different season.
The 3.21875 was the true value for the exact. I figured that was the error with the percent difference.
Yeah.
But this is the true value?
Yeah.
Okay, so the book is wrong? No. Oh yeah, book is right, but we were wrong. We had some other value. Anyway, so this is there for y Euler. Okay. We are writing y at I plus 1 equal to yi plus the value of the function f of xi comma yi multiplied by delta x. We are applying that to the first point, okay, which is, what is yi here? This is your I, okay, this is your I plus 1. So I and then I plus 1. So what is yi? 1. It's the value of y at point I, so 1. And what is the value of the function? By the way, this is y exact. The value of the function is f of x comma y equal to minus 2x cubed. I have to write the problem in reverse now. Plus 12x squared minus 20x plus 8.5. So I have to write y Euler is 1 plus minus 2 times x cubed plus 12 times x squared minus 20 times x plus 8.5 multiplied by my step length, which is 0.5. Just to keep it a little clear here.
Should you be getting 1.625?
What did I do wrong now?
And I think it's notation because I got the same thing.
yi plus,
So your y Euler, the first one,
yeah,
you need to set your initial condition. I thought the initial condition was 1, and then the first of that was 0.85 because.
yeah. So it has to be based all on this. Yeah.
But after that, then you can auto.
So thank you. So the y Euler at this point is all based on the x value here and the y value here. So this has dependencies only on the previous row, not on this x value. So you can just calculate this further. And in Excel, the cool thing is you can just do the automation pretty effortlessly, because at each row, the values depend on the previous row and not on the current row. So you can just drag the formula down all the way to the end. And you can also compute the percentage difference as 1 minus Euler divided by exact multiplied by 100. What are we getting here?
Creates another error.
No. Thank you for the suggestion, but no. E4 minus D4, D5, D5 minus E5. So we are getting these two values correct, but what's wrong with our error formula? Okay. Hold on, let me try again. 1 minus this divided by this multiplied by.
Yes.
Say it again.
Isn't 63.1 the correct error?
Yeah, but the later values don't seem to agree with what the book has. That's why I'm looking at it.
Mine do.
Actually, wait, hold on. Actually, what the book calls as global error agrees. It's what the book calls as local error that doesn't agree. So this is, according to the book, global error. But whatever you call it, what I want you to get is that at a given point, here is the truth, and here is what you get, and the difference between them. Okay, that is important. That is whatever is the correct value or expected value, and you are overshooting it by 2.5. So the difference being 125%. That is what you should understand. Always, whenever you have the exact solution, we want to go for absolute error, which is comparing the predicted with the truth to get a percentage difference. Okay. So keep this sheet. Okay. Those who are trying, please keep this sheet. We are going to try the same problem with better and better methods, and then we'll see how this percentage difference changes. So I'll give you a minute to do the work and tell me if we are ready to move on. Okay.
Can you just play the why again?
Euler, yeah. So Euler involves the previous value of y and the value of the function y computed at the previous value of x. Or actually, this is current, this is forward. So this is I, this is I plus 1. So current and forward. So if you're trying, I want you to make sure you and I are on the same page here before we all move on together.
So if we were to like actually want this like regularly, we're not gonna be getting y exactly.
Yes.
Okay, so we just get rid of that column if we want it to be general purpose.
If you want it to be general purpose, there are ways to estimate the error. So this is computing the error where you know the truth. If you don't know the truth, we'll have to estimate the error, which we will see when once we have seen all the three methods. We'll see the error estimation for all of them together so that you know how to do it for each method. One thing is for sure, you will almost never use this method because it's a very crude method. It's one of the least accurate there is. Are we ready to move on? Yes, no, those who are trying, thank you. People in the back who are trying, can we move on? Are you able to get all up to here? Good, thank you, thank you. All right, good. So now, like I said, this is a very crude method. And if you refer to figure 25.2, if you refer to figure 25.2 in your book, let me, yeah, I can just draw it for you. So the Euler method works like this. You have your x value, let's say this is I, and at that point you have a yi, and then the next value of yi plus 1, suppose the truth is here, okay, this is truth. According to Euler's method, you don't get to go here, you get to go here. Yeah, I've drawn it too well. You get to go here, y Euler. Why? Because it's based on the distance and the local slope. So this is your delta y. You can see that this is the difference between, or this is the gap between the truth and what the Euler method will predict. Okay. Now in this case, when do you think your Euler method will actually be a good way to solve problems? Want to say something?
I guess, with the sufficiently small depth or step between your x's, but that applies to every thing really.
So if you make your very fine delta x, that is if you chop your segments into very fine segments, anything will look like a straight line. You resolve it small enough. So in the limit of making the delta x small, that is good, but that also comes with storage constraints, meaning you have to store a lot of numbers, and it also comes with computational cost, meaning you have to do more operations. So I guess it is a solution, but not always, because it has practical limitations. Which other situations can this actually be decent? Yeah.
This should work like relatively often. We shouldn't have a ton of problems.
When?
Like, it's assuming we just have a function, we don't need much else for this to work. So.
No, it will work. The question is, when will it work correctly? Did I hear something? When your function is linear, of course, when it's linear, this method is exact. When there are no second order derivatives, this method is exact. But if it's a linear problem, why would you need numerical methods, right? But there is a caveat to that. There are many curves which are kind of linear in a very local region. They are not globally linear, but in a certain region they look almost linear. For example, if you take e power x, the exponential function, okay, you can graph it, x equal to 0, it just starts at 1 and quickly becomes very large, e squared, e cube, and so on. But for very small values of x, if you also draw the curve 1 plus x, you will find out that e power x can be approximated as 1 plus x if x is small. You know this, don't you? You have always done approximations of the exponential for using only the first two terms or first three terms when x value is small. So whenever you have functions which locally are linear, which don't have significant higher order terms, it's okay to use this method. That is, whenever you have dy by dx equal to f of xy, and f of xy is sort of linear in a very limited range, in this range at least you can use the Euler method. So what is the key here? You have, as soon as you receive a differential equation, you need to graph it and see which are regions which it approximately behaves like a linear function. So going back to this function here, minus two x cubed plus 120x squared minus 20x plus 8.5. Can you guess which range of x values would it approximately be in? You, sorry? If you take that function, if you take x values less than 1, if x is say 0.1, x squared, x cube are even smaller. So for x values less than 1, the top function is probably dominated by minus 20x, less so by 12x squared, and even less so by minus 2x cubed. You can agree with me that you will, but the art lies in looking at a function and then going which are regions in which I can approximate this as a linear function, like you said. It's a linear function, and so I can use the Euler method in a very limited region. Now, what is the big upside with the Euler method? He said that already. It's a very simple method. If you can understand where to use it, you can actually use it wisely. If you indiscriminately use it everywhere, it's a very error-prone method. Okay, so you have to be careful. And we'll see more accurate methods. Okay, so let's continue this on Thursday, where we'll try to go through the higher second order methods and then fourth order methods. Okay, thank you.